All right, so today I'm going to be working on the rest of Chapter 2, going from Section 2.7 and focusing on Section 2.7 and 2.8 in particular. Again, Chapter 2 is kind of large, but with that, we're also going to move on into Chapter 3, but I'll probably do that after the break. But that being said, here's the deal. If you come over here to your assignments, what do you have due for me? Just want to make sure you guys are aware of it. You got your homework number 3. When is it due? 13th, which would officially be, because of fall break, our next class, right? So this would be due at the beginning. The online homework is due at the end of the day that day. I always put it at 11:59. But the traditional homework is actually due right before class. You will be turning that part in. So Jacob can actually take that stuff for you guys. So hopefully you haven't had any problems with that particular homework set. If I click on it real quick, you can actually take a look at it here without having to download it. Okay, some of the problems should be very straightforward. Hopefully you've already done most of it, if not all of it at this point, because we've already covered all the materials with this stuff. So I gave you a couple of 4 particular matrices. I want you to find, negative 3a, b minus 2a. This is the matrix algebra, making sure you can manipulate matrices and stuff like that. I want you to find 5 times I2. Now, who is I2? That's the identity 2 by 2. That's our code for that. And then minus d and 5 times identity times d, 2 by 2 there. All right, and then you know that a times b does not equal b times a traditionally with matrices unless we force them to do this. So I have a matrix A here, and I got a matrix B here with a k value as k. And I want you to play the algebra game of multiplying a times b, multiplying b times a, and try to figure out the value of k that actually would make the matrices commute with each other. A times b equals b times a, okay? Again, I want you to verify, which means show that a times b equals a times c, but b doesn't equal c. Clearly, b is right here. C is right here, and they're not equal to each other because matrices to be equal to, each entry has to be the same. But then I want you to show you that a times b will give you one matrix. A times c will give you the same matrix, but you got to show me that by showing your work and stuff like that. So here's a classic example of a times b equals a times c, but b doesn't equal c. So you don't always get that property like we do with integers and things like that. So for 3a through 3c, 3a, 3b, 3c, I want you to find the inverses of these matrices. Now, 3a is a 2 by 2. We got a special formula for calculating the inverse of a 2 by 2. You remember the 1 over ac minus bd type thing here, and then you got to switch the main diagonals and negate the off diagonals. It was a formula. Go back and look at your notes. But with 3 by 3s, which the other two are, you have to augment those things with the identity, row reduce the B matrix to the identity, and what it's going to be augmented with will actually turn into the inverse. So show your work on that. Again, this is a 2 by 2. I want you to find the inverse of this guy, and then I want you to solve the equations ax equals b1, here's b1, here's b2, here's b3 and b4. I want you to use that inverse that you found in this guy to actually solve these matrix equations. I'm trying to get you used to what the purpose of the inverse is going to do here. So you got a, x equals b. I got to multiply by a inverse, if it exists, right beside a, and the only way to get to a would be multiply it on the left. So what you do to the left of ax, you've got to do the left of b1 or b2 to be able to get your actual answer and stuff like that. Okay? This one right here, I want you to partition these guys. This is that partition stuff we were talking about. I partitioned A. You don't have to do any more work to A. But over here, B, let's see here. A is what? 3 by 1, 2, 3, 4, 5. So this thing's got to be 5 by, well, this one happens to be 5 by 4. But how should you partition this guy up? And you should break, I'm going to give you a hint, you should break it into like 4 little blocks here to be able to multiply these things out to be able to get A times B with these submatrices and stuff like that. So just getting used to the idea of partitioning up and show you that it kind of saves you a little bit of time with that because it's easier to basically multiply small matrices than it is to multiply a big matrix times a big matrix. So the purpose of your partitioning stuff here, okay? All right, and then the rest of them show that I squared equals I, so that's very easy. You just do A times A, that's A squared, and watch the identity pop out. So there's a problem where the inverse is himself. You've got a matrix that it's its own inverse, so just something like that. And so, and again, some of the, I want you to kind of look at some of these questions because these are theoretical questions. In terms of partitioning, remember this one's got that upper zero thing here. We talked a little bit about that. And you got this form of A0 CD for M, and the M squared equals the identity there, okay? So make a 2 by 3 matrix to show your construction of how to compute the, basically, and show your construction works by computing what M squared is. So again, something to play with. It's more of a theoretical question there. And here's another one right here, and I promised you these guys on the test, the LU factorization, decomposition type thing here. This one, I gave you A, and I gave you its LU decomposition, okay? So you want to verify. All you got to do to verify is just multiply L times U, and guess what you pop up? A. Show me that works. Show your work. Now, on this one here is, I want you to find the LU decomposition. And remember, you do them at the same time. You basically find L, which is your lower, and at the same time find U. We have some great videos on me doing that, so practice those problems and stuff to make sure you can get your LU. And don't forget at the end, to make sure you didn't make some bonehead careless error, this is why part 7 was in here. Remind you to multiply L times U, because we all make mistakes, so just double check yourself. And you can double check this on the calculator is what we're telling you here, so there you go. All right, and then this one here is, again, we're going to solve this AX equals B, but I want you to do the using the LU factorization of this guy, okay? So find the LU factorization of this guy, and then remember this procedure that we did to be able to solve for X. So it's AX equals B. And the whole purpose of this is to actually save some time. Now, again, we're looking at algorithms for computers that actually do this type of work for us, but it actually, when you do the LU factorization on a particular matrix, it actually saves, it's less time in terms of the number of operations that need to be calculated for the computer and stuff. So there you go. So there you go. And there's your section 2.1 through 2.5. Probably over this weekend, I will be posting the next homework set up for you guys, because you can't have not without a homework set, but it'll be posted in the future because it's on the material that I'm doing now. Question? Yes, it is. Yes. So I'll blow it up with you. Oh, maybe that's not really helping me out any. Oh, let me do this. I'll just do this. I'll just download it. Sorry, it'll be easier for me to do it, not on the actual screen itself. So there. So what was it, number 5? On matrix B. Yep. That is a 3. There you go. It is a 3. In case you're, all right. Okay, other questions? All right, so let's get started back over here with our material and stuff. So let's go back to our home screen, and let's start on today's awesome lecture. Well, today we're in section 2.7. And my goal is to do 2.7 and 2.8, which is an incredibly important section there. But then 2.9, 2.10 will go rather quickly. So 2.7 is application to computer graphics. So this is more of a theoretical, what can I do with this stuff, especially for my computer science and my graphic engineers and the ones that do a lot of work with computers and stuff. So here's an example. And again, there's not much I can do in terms of showing you kinds of problems on this thing, but here's an example. So I kind of wrote this thing out, and I did copy it out of the textbook to give you the idea, but we got this nice bold-faced N looking thing here. And now we're trying to, basically play around with the fonts, trying to make this stuff look fancy or whatever the case may be. And so if you look at N, I've got these 8 nodes on the N. Nodes are places that are basically vertices. They're vertices on the end, sharp turns on where I actually draw this thing out. This is a bold end, so I got, there's 1 vertice, 2 vertices, 3, 4, 5, 6, 7, 8. So there's 8 vertices, and I connect back down here to 1, and that creates that bold-faced end-looking thing. And what I did over here was, you can look at them as vectors, you can also look at them as points. So 1 is at the point 0, 0, 2 is at the point 0.50, 3 is at the point 0.5, 6.42, 4 is at the point 60, 5 is at the point 68, straight up there vertically, 6 is at the point 5.58, 7 is at the point 5.5, 1.58, and then 8 is at the point 0.808. Okay? So we got this nice little end thing here. What do transformations do for me? So you can now take these coordinates and put them in a matrix. As a matrix, this thing is now going to be what? It is 2 by 8. Agreed? All right. In the matrix, the columns of the matrix are actually the points, or you can also look at them as vectors. Okay? Now, we're going to do what we call a shear transformation. Remember before I gave you all these different types of transformations. Shear transformations that stretch and shear, which shifts it to the right or to the left. I have some things that dilate, some things that expand. We went through a bunch of different, mainly 2 by 2s are the ones I focused on, matrices. We also have one that, sine, cosine, negative cosine, sine. I have one that actually did rotations of particular transformations and stuff like that. So we introduced those in previous sections and stuff. So we're going to do what we call a shear transformation. And if you'll notice this thing over here, you got ones and diagonals, so it's kind of like the identity there. But over here in the upper right corner, I got a 0.25 and a 0. Now what this shear is going to do is going to take this guy and kind of shear it or move it, shift it to the right a little bit. I mean, just the base will be the same, but you shifted the top over so you get the shear look to it. Okay, and there's my shear matrix transformation. So if we multiply A, this is what I call A, this is your transformation, the shear transformation, by N is where the points are at, N representing the N. So we get an AN, which will give us a matrix of a new vertice. So I went ahead and did this for you. A times N. Let's see, A is 2 by 2. N is what? 2 by 8, right? So we're going to get a AN, which is a 2 by 8 matrix. And what it does is it actually shifts or shears this N, so it looks more like a cursive N type thing here. Again, this section is called, the applications in computer graphics. What can we kind of do with this stuff? There's a lot of things you can do with this stuff. I mean, especially this day and age where you guys have computer games and computer animations and all these other things. One of my senior projects that I had this past year was on a person who was double majoring in mathematics and graphic art over there in the other side of campus there. And so, awesome, cool, because it's really cool to see math used in not just engineering and physics and chemistry. It's actually used in other areas as well, graphic arts. So they were working on, graphic designs and making these transformations, and especially working with video games. How do you make that gun go boom and make it look like the zombie blows up and the weird entries and fall out of this guy? There's really cool computer graphics, but to be able to do that, basically there's a lot of math going on behind the scenes with this stuff. And the other thing is the angle at which you actually have to, hit or whatever, the thing has to make it look a little bit different. And the different angles of when you have light in the virtual room there, and how do you get those shadows and shades to be lit? There's a lot of mathematics going on in this computer graphic stuff. So this is just an example. And you can look at this thing and go, wait a minute, now that looks like a good end, but that looks like too fat of an end or something like that. Well, no problems there. So you can create another transformation that maybe wants to shrink this thing in a little bit. Maybe it's too large and you want to shrink it down a little bit. So I'm over here on my next page here. Now the x coordinates are, bad wording on my part, T-O-O there, okay, too large, all right. Too much math in my world. Now, the x-coordinates are too large, and you want to scale back those x-coordinates by 25%. This picture was just bad. It was just way too large on this thing, so we want to scale it back a little bit. Well, we have another transformation for that. So you want to scale back the x-coordinates by 25%, meaning you want to scale the x-coordinates to 75% of their original size. Does that make sense? To scale back 25%, you still want 75% to be left over. So there's where that 0.75 is going to come from. So you multiply each x-coordinate by 0.75, and you got a transformation. We'll call this the S transformation. Notice it's the identity, 1, 0 on the diagonal, 0 is off the diagonal. But in that 1 where the x-coordinate is at, you put a 0.75. That's going to scale it down by 75%. Does that make sense? So you're losing 25%, if you will. And so you can do this S times A, and so S was the new transformation. A was that original transformation that did the shear. So you can combine two transformations to create one big transformation over here, which you get the transformation of 0.75, 0.187501. And all I did was take one of our classic transformations that we talked about in previous sections about what we can do with this stuff, and multiply these two transformations together to do a combined transformation, okay? So row by column, 0.75 times 0, 0.75 times 1 plus 0 times 0, that's where the 0.75 comes from. Second row, first row, second column, 0.75 times 0.25 plus 0 times 1. 0.75 times 0.25 is where you get the 0.1875 from. 0 times 0, 1 times 1, 0, 0 times 1 is 0, 1 times 0 is 0, so 0 plus 0 is 0. And then row by column, 0 times 0.25 plus 1 times 1, you get 1 out of it. So this is a combined transformation that does both. So it actually takes those original coordinates, shears it, and shrinks it down so you get another awesome looking, and it looks a little bit thinner. I'm sorry, I'm doing my hand drawing on this thing. So I get an N, but it's not as fat and not as tall in terms of the scaling of this thing. So there's lots of these weird, interesting transformations. And then this is just working on a letter. Can you imagine what you can do with, game theory where you have a lot more variables that you're actually playing around with and stuff like that? So, but again, this is all theory. I'm not going to be hitting you guys very hard on this particular concept. I'm just trying to show you why this class is important, okay? So, with this, again, you've got a lot of information that's actually going on with this stuff. The other thing is this. We're going to do something called a homogeneous coordinates, okay? Now, what we're really telling you is this. Now, you may be looking at, a two-dimensional graph picture. Two-dimensional, x, y axis is all you got. Well, we're going to expand that into the third dimension, okay? We're going to throw an extra dimension on this thing just to keep a placeholder for what we need. And that extra dimension will allow us to do things that we typically couldn't do if we only focus on, for example, the world of R2. So you can actually expand R2 into other areas and keep focused on the R2 because that's what you see, but there's other dimensions going on behind the scenes that you don't see, okay? So those are called homogeneous coordinates. So let me talk about that for a second. Again, this is a big talk. Don't worry. I'm going to actually hit some problems and do something with you in a second, but this is just theoretical questions here. So here is what we mean, definitional-wise, as a homogeneous coordinates, okay? This is still under that computer graphics concept within the world of linear algebra, all right? So what we're doing here with these homogeneous coordinates is we're changing from a standard Rn, whatever space you want to play in that actually represents the variables of the games that you're playing with, to an Rn plus 1. You're going to add on an extra dimension, okay? So here's the idea. Blow this thing up, you guys can see it's a little bit better in the back here. So here's your idea. So if we have a point vector, if you will, x, y in R2, we can identify the point, the vector, with a new point slash vector, x, y, and I'm just going to put a 1, and we'll make it 1 in R3. And this could be any constant. You don't have to do 1. You can do 2, 3, or whatever. So you can have different layers of this thing if you need to. But just 1, okay? Again, or any constant. So we just made it another third dimension. Why would you want to do this? Well, I'm going to show you, okay? So definition here is this. We say that x, y has a homogeneous coordinates in x, y, x comma y comma 1. You can see the x, y. You can see the two dimensions even if we go all the way to the third dimension. The first component and the second component are the first two dimensions on this thing. So that's what we say what we're talking about when we talk about a homogeneous coordinate system within R3 or R27 when I'm only focusing on R26. You know, you can do this a lot why would you want to do something like this? Well, again, something behind the scenes. If you're doing like screenshots you've got motion. So people talk about the fourth dimension, for example. What exactly is the fourth dimension? Okay? Well, the third dimension is what you see three-dimensional space around you. The fourth dimension would be motion within 3D. So you can put a time element. Time 1, I'm here. Time 2, I'm here. Time 3, I'm here. As I'm moving across the spectrum, or whatever the case may be. So you can sit there and talk about the fourth dimension, but you actually see the fourth dimension, what you kind of do with the actual movement within the third dimension. And then you can go in fifth dimension, sixth dimensions. You know, this becomes more mathematical, but it's actually coordinates behind the scenes. So if I do screenshots of the fourth dimension, they're going to be in 3 dimension. So that extra fourth dimension is going to be at time 1, time 2, time 3, but you're only viewing the 3-dimensional object as it's quote unquote moving and stuff. Question? Yes. Well, okay, so what it's, not really, but that idea is going to come in a second. Hold on, that's actually a good question, but what we're really doing here is we're just adding on another dimension so we can play better algebra with this. So let me show you. Now, for you guys that have had Calculus 3 before, awesome. You guys that haven't, I'll pick on you for a second. All right, so let's talk about, for example, this is R2, okay? We got ourselves a point right here. This is the point, we'll just call them arbitrary x, y. I went over x on the x-axis. I went up y on the y-axis. There's my point, and you can also think of them as a vector from the origin type thing here. But basically, point or vector is the same guy, the x, y, okay? Now, if I convert this thing into R3, 3 dimensions, and this is where we talk about graphing in 3D, is what we do in Calculus 3. Okay, so I have the x, y, and then we throw in the z plane on this guy. So we got the z-axis. So now points are going to be x, y, z. So what we're talking about here, if we talk about R3, we're going to look at this homogeneous coordinate point here of x, y, and we're just going to go up 1. So there's a plane up here. Z is 1. So I'm going to sit there and declare this guy. Here's 1 right here. So if you look at this, there's a plane right here at the level of 1. Now we're going to take this xy plane, and so here's x. We went over x, and we went up y. So here's the point, but it's inside this plane that's at the level of 1. So here is your x, y, but it's in the 1 plane. So we talk a lot about planes in Calculus 3 and stuff. So we lifted this guy up 1 level. And that little 1 is going to help us out when we start to try to do some extra manipulations of these coordinates, like the shearing and things like that we were doing before. And you'll see that in just a second here. So, go back over here. But this is the idea of taking this. If you think of, this is your XY plane, so this is being handed to you. So the X goes this way, and it's sticking out of the page right here. Here's your Y-axis, so that part comes over here. And then you got the Z-axis, does the lifting and stuff. You go up just 1 unit up here. So you're inside this particular plane, but it does make a 3-dimensional vector, if you will, or point. So, back over here. Again, we say that xy has a homogeneous coordinate in the system of xy comma 1. But notice now this is 3 dimensions. This is an element of R3, vector in R3. The idea is this. The vector or point has not changed, but we just want an extra term on it. Why? Well, let me give you an example. Here's an example right here. Now, in R2, we want to create a transformation that takes x comma y and we're going to do x plus h, comma, y plus h. So what are we doing to this particular point? We are going to shift it, to the x, you're going to add h to it, so you're going to shift it right, and you're going to y plus k, you're going to shift it up. You're going to shift it to the right, h, up, k. We're shifting the point over. Does that make sense? You shifted the x coordinate by h, you're shifting the y coordinate by k. So x, y is going to now be mapped to x plus h, comma, y plus k, where h and k are some kind of constant, or some kind of number we came up with. Now, how am I going to do this? And I want a transformation that's going to help me do this, okay? So if we look at the homogeneous coordinate system here, instead of looking at x, y, going to x plus h, comma, y plus h, this would be now x, comma, y, comma, 1, going to do x plus h, comma, y plus k, comma, 1. That just 1 stays the same. That allows me to play in the world of 3D, R3. Does that make sense? So look at this particular matrix right here. It throws on an extra column on this thing for me. So here's your x, here's your y, here's your column, the third dimensional column. Now, and now that this has to be 3 by 3, because we're now in R3 going to R3, but my original point was x, y, 1. But if I look at this matrix, this transformation here, 1, 0, h, 0, 1, k, 0, 0, 1. Now, let's multiply this matrix times this vector. 1 times x plus 0 times y plus h times 1, row by column gives me x plus h. 0 times x plus 1 times y plus k times 1 gives me 1y plus k, y plus k. And then 0 times x plus 0 times y plus 1 times 1 gives me 1. So I'm still back in that same level, 1. And notice that this matrix allowed me to go x plus h plus y plus k, comma 1. It allowed me to do that shifting of both the x and the y coordinate, but I needed that third dimension to be able to do this. So this idea of the homogeneous system allows me to do this. And we still, when we look at these guys, that 1 is actually meaningless because we're really focused on the R2 result as we look at the graph of this guy. And so x, y went to x plus h and y plus k. That's the reason behind this. So you get this extra manipulation you can do on your graphs to be able to get the things you need to be done to be able to do your graph stuff. So sometimes you need to add on an extra dimension to, even though you're focused on 2 dimensions or maybe focused on 3-dimensional objects, you want to basically do something with those 3-dimensional objects that a traditional transformation won't do. But then if you go to these quote homogeneous coordinates, just adding on a constant over there gives you that 1 extra dimension to be able to manipulate those other vectors and stuff and get you what you need to do. Again, this is the theoretical stuff of why this matrixy stuff that you're studying is important, okay? So let's keep going here. More stuff. All right, what about some of these transformations? Well, again, I want to remind you of some of them here. In general, any R2 transformation is given by, remember, any linear transformation can be represented by a matrix. If you learn anything in this class, learn that. That's why we're going to be talking about a whole chapter to talk about transformation stuff here. But at the end of the day, remember, it's being represented by a matrix. That's why we're doing all this matrix stuff in the beginning. So any R2 transformation can be given by T of x is equal to A, matrix A times x, and can be written in a homogeneous coordinate by the block matrix of the form A0, 0, 1. A was the original transformation in R2, but we can throw on this extra little 1 down here on the corner, and now we're back into R3 because we now have an extra dimension on our particular vectors and stuff. So, if you remember some of the transformations that we talked about before, here's a big one right here. The cosine of phi, sine of phi, 0. This is x, y, and then 0, okay? And remember how to create this guy. What's the derivative of cosine of phi? Negative sine of phi. What's the derivative of sine of phi? Cosine of phi. What's the derivative of 0? 0. So the first column is basically cosine, sine, 0. And then your second column will be its derivative. That's how you can memorize it. And then the third, to make it into this R3, is that 0, 0, 1, to put that 1 down here in the corner. So this is my classic transformation of rotation. You tell me what the angle phi is, and this matrix will rotate whatever vector you got in R2, rotate it around and still be back in R2 by a factor of counterclockwise rotation by the phi angle here, okay? So there's one right there. So you've just created a matrix that in this basically R3 that's going to do the same thing to the first two vectors and leave R3 there. Yes? Yeah, so this one in the bottom is just there as a placeholder, but that's what they call the, like I said, the homogeneous coordinate system here. So you're just going to leave that one there, but it allows us, that row by column, we can manipulate that one to help us shift or add h to it like we did in that last problem. It allows us to do a little more things than we could have done just by focusing on just the 2 by 2. This is what that homogeneous and that computer graphics aspect that's going to do for us. But you're right, that one is just a placeholder there. This is still, our focus is on, in this example, R2. We want to manipulate R2, but we want to do more things to R2 than what traditional 2 by 2 matrices will allow us to do. So by putting that one down there will allow us to do a few more things and it still be a transformation. It still follows those aspects. Yeah. Yes. It does. It does. It scales the x and stuff like that when you multiply it out, and it just puts it at a different level. One is typically where you want to go when you want to do like a transformation of x to an x plus h. You need that one down there that you can put the h in there. H times 1 puts the h's on there. To do a 2, you would have to do an h divided by 2 to scale it. It doubles it, but then you got to scale it back a little bit to get the h back in there. You can still manipulate it. It'll still work. Just makes more work for you to do and have to outthink the question. All right, continuing on here. This guy here, if you remember this was the matrix, the 2 by 2 matrix, 0, 1, 1, 0, that rotated around the y equals x axis. It basically flipped the x and y coordinates for you, okay? But now this would be 1, 0, 0, 1, and then that 0, 0, 1 down at the bottom, it's still the same thing. We're just putting zeros here, zeros there, and one down in the corner, so it's not going to really do anything for us. This is still going to be reflecting about the y equals x axis in that R2. It does the exact same thing, and it will keep that 1 in the coordinates there. And then the third one, this was your scaling factors here. You scale the x coordinate by s, you scale the y coordinate by t. Remember we put 75% on that thing and multiplied it. It knocked it down by 25% there. Whatever percentages you want to put in there, you want to make them bigger, make s bigger than 1 or whatever. But this is it, and if you put a 1 down there, it's still going to do the same thing. It's going to take the x coordinate and basically scale it by s, and take the y coordinate and scale it by t. So we're taking those same transformations, which I went through the book and actually printed them out here for you, show you all those different transformations you can do. All we're doing is adding on 0, 0, 1, 0, 0, 1 on to make it an R3 instead of an R2, but it allows me to do more things within those transformations. So, okay. So, again, this is just theoretical stuff. What kind of questions am I going to ask you on this stuff? Not much, maybe. I will probably ask you to transform something or other, so be familiar with something like this, but not too many questions on it. This is a section of why are we studying this stuff type of thing here. So, last little bit of section 2.7, composite transformations. All right. So, I at least wrote out an example for you guys. I didn't make you guys do it. I wrote it out and want you guys to get it in your notes. So, copy along here. Here we go. Composite transformations. Find a 3 by 3 matrix that corresponds to the composite transformation of, here it is, scaling x and y by 4. What does it mean by scaling it by 4? You're going to do 4 times the size. You're increasing it by a factor of 4. Scaling it by 4. And then rotating the coordinates 90 degrees. So you want to take the x coordinate, rotate it 90 degrees, the y coordinate, rotate it 90 degrees. So your angle, phi, is going to be 90 degrees, rotating it, okay? And then transforming the coordinates by which adds 2 to the x coordinate and -1 to the y coordinate. So you'll notice here that they're still talking about x by 4, y by 4. We're going to rotate the thing by 90 degrees, and then we're going to add 2 to the x coordinate and negative 1 to the y coordinate. So any point x, y, you add 2 to x plus negative 1 to y. And then what would that do for me? Well, here's the problem. I could scale it, no problem at all. I can do that in 2 by 2. I can rotate it 2 by 2. But to actually add those coordinates, shifting the coordinates over by 2 and down by 1, x coordinate by 2, that y coordinate down by 1, that's going to cause me to have to go to the R3. So it's really that third one that makes me go to this R3 thing and going to do these, quote, homogeneous coordinates type thing here. So instead of your classic XY, I need that coordinate system XY1 on the homogeneous. You still got your XY, chunking that 1 on there. This is what we're focusing on, those homogeneous. Now, again, looking at the same models that I just put up here a few seconds ago, what would the scaling be? That was the ST. We're going to both scale x and y by 4, so that would be 4, 0, 0, 0, 4 again, 0, but then you don't really mess with that third column, third row here, 0, 0, 1, okay, because that just puts you into this world. All right, the other thing is we want to rotate this thing by 90 degrees. That means my phi is going to be 90 degrees. So I go back, and again, just to show you, I'm actually using these guys here. So this is my scaling. This is a 4 and a 4 and a 1, so that was the matrix that I used. So for the rotation, phi is going to be 90 degrees. So I just wrote it like this, you can see it. That's going to be the cosine of 90 degrees, negative sine of 90 degrees, 0. Sine of 90 degrees, cosine of 90 degrees, 0, and then your 0, 0, 1. This is what's going to rotate your coordinates 90 degrees. And then the last one, if you remember, was that HK thing that we did on that first example, where H was 2, we're going to shift it over by 2 on the X coordinate, and your K is negative 1, so it's 2, negative 1, but then your last row is at 0, 0, 1. So this is the matrix, identity across here, putting the 2 and the 1. That's what adds 2 to the X's and actually adds negative 1 to the Y, okay? So we've got 3 different matrices that we're doing here, so 3 different transformations times your homogeneous coordinate system, X, Y, 1. Now, for this guy, I just went ahead and just made it simple for you. What's the cosine of 90 degrees? 0. What's sine of 90 degrees? 1. With that negative out front makes it negative 1. That's 0. Sine of 90 degrees is 1. Cosine of 90 degrees is 0. That's a 0 and 0, 0, 1. So this matrix really becomes 0, negative 1, 0, 1, 0, 0, 0, 0, 1. So you multiply this matrix times this matrix times this matrix, and I did that for you guys, leaving the X, Y, 1 down here at the side, and it created this particular one big transformation. You can do the composite of 3 different transformations and create one big matrix, which is one big transformation that does all 3 of these things that you want, and you end up getting this matrix here. So I have to take my word for it, but I've multiplied this for you. So if you take the matrix 4, 0, 0, 0, 4, 0, 0, 0, 1, times 0, negative 1, 0, 1, 0, 0, 0, 0, 1, times 1, 0, 2, 0, 1, negative 1, 0, 0, 1, you're going to get this matrix here. 0, negative 4, 4, 4, 0, 8, 0, 0, 1. And then you multiply that times X, Y, 1, and that's going to give you your coordinates. Now let's finish this thing up, but first I got a question. Yeah.
Like in the previous chapters where we could multiply or do added addition with 2 different types of matrix, like a 3 by 4 and a 4.
Yeah, they had to be the same size. That's right.
But if we add the 1, we could just now compute those.
Right, through the multiplication, because of that 1, that row by column type thing here. So if I just focus on this right here, look at that first row. 1 times X plus 0 times Y, but that extra 1 down there allows me to add constants. Plus 2 times 1, that gives you X plus 2. Second row, 0 times X plus 1 times Y plus negative 1 times 1. That's 0x plus Y, so that's Y minus 1. That took Y and then shifted and left 1 unit. Does that make sense? But I had to do that. It required me to actually add that extra dimension. That's where the homogeneous system comes from. And so, just to show you what you get here, when you multiply this thing together, you're gonna get one big vector. What vector would this be? Row by column here, this would be 0 times x plus negative 4 times y, that'll be negative 4y, plus 4 times 1, that would be plus 4. Second row, first column here, 4 times x, that would give you 4x, plus 0 times y plus 8 times 1, that's plus 8. And then 0 times x plus 0 times y plus 1 times 1, that's 1. There we go. I get negative 4x plus 4. I get 4x plus 8. And I get 1. Now, in terms of my coordinates, you can, again, you're looking at this transformation here, but the idea is this. We're really only focusing on those coordinates x, y. So where are x, y going to go to? They're going to go to negative 4y plus 4 and 4x plus 8. And this would have the effect of taking this xy coordinate, scaling it by a factor of 4 for both the x and y, rotating these coordinates 90 degrees counterclockwise, and then basically shifting it, basically translating it by adding 2 to the x coordinate and subtracting 1 from the y coordinate. And this is the new coordinates you get. And you get to see it here, even though this is a three-dimensional vector because we're in R3 on the homogeneous system here, but we're really focusing back on R2. So you get to see one system inside of a bigger system. That's very helpful in terms of the computer graphic stuff. Yes, ma'am. No. Well, yeah, yes, it does in terms of this. Okay, to answer your question, yes. Okay, so let me go back in terms of this, because remember, A times B does not equal B times A. So yes on that. So traditionally, they're going to give you the order that they want within the problem. So you just kind of focus on the order. So if you remember the question, what it said was this, okay? Find a 3 by 3 matrix that does this. Now, the first thing was you're scaling x and y by 4. That's why this matrix showed up first. Comma, then you rotate it 90 degrees. That comes the second term. And then you want to transform the coordinates, which adds 2 to the x and negative 1 to the y's there. That's what the matrix that does this. So yes, the order does matter, I mean, in terms of this. But, you know, when you're doing these particular problems, you kind of do them the way they're described within the question. Does that make sense? So because A times B is not equal to B times A. So if I switch these two guys, that would be, you know, rotating and then scaling out by a factor of 4. Now, in certain cases, it won't matter because it would actually do the same thing to the coordinates. But if in a lot of cases, it will change it. So you always want to do it in the order because you're not sure. Do it in the order that they describe to you. Does that help? Okay. All right. Well, again, I know this was theoretical stuff, but that's kind of what I wanted to talk about with this stuff because that is honestly what section 2.7 was about. But for you guys, and again, the reason why the last time I taught this class, I didn't go into this as detailed as I did with you guys. But then first day of class told me I was in trouble when I wrote, how many people are engineering majors? Nobody raised their hand, except a couple of them. Computer engineering, right? What's your major? Oh yeah, finally I got a mechanical in here. One. That's so sad. Okay. How many electrical engineering majors? How many math majors? Oh, thank God. Here it is. Yay, 3. Okay. How many computer science majors? Yeah, exactly. Everybody raises their hand. That's why I went over this stuff, because I wanted to see you guys actually get a hold of this thing a little bit deeper, because the last time I taught it, I had more mechanical engineers and electrical engineers and math majors in my class. But this time, I got more computer science folks in my class. So that's kind of the idea of why I wanted to kind of focus on this. So let's pick up now with section 2.8. Now, this is for everybody. This is something we can actually get a better handle on, and that is subspaces. This is, again, a very important concept here of actually doing the problem stuff. Let me slide this under here. So get my papers here. All right, here we go. Subspaces of Rn. Now, definition. A subspace of Rn is any set H in Rn that has 3 properties. 3 properties. A, B, C. 3 properties. To be a subspace, the zero vector has to be an H. So first off, you've got to set Rn, R3, R5, R102, I don't care, R somebody, okay? And H is a subset inside of Rn, and it has these properties. The zero vector is in H. So, you know, in R3, the vector 0, 0, 0 has to be inside of H. We know it's inside of R3, it's got to be inside of H. In R5, 0, 0, 0, 0, 0, it's got to be inside of H, okay? Zero vector has to be in there. The second one is something called closure. If you have two vectors, U and V and H, then when you add them, U plus V, it also has to be an H. Now remember, H is a subspace. It has a special property, more so than what the property of Rn has. It's got something special about H that puts you in H inside of Rn, okay? So, but when you take these two vectors inside of H and you add them, you'll be back. That's called an element of, in case you want to know the symbol there, element in H. You'll get to see a lot more mathematical symbols in this area here. So U plus V is going to be an element of H. Okay? Continuing on, part 3. For each U in H, and you pick an arbitrary scalar, typically the scalar, since it's coming from Rn, is going to be a real number. The vector, that constant C times that vector U also has to be inside of H. So it's closed, two vectors inside of the set. When you add them, have to be inside the set. And the second thing is scalar multiplication. You multiply a scalar times any vector inside the set. That new vector is going to be inside the set. That is what creates a subspace. The zero vectors in there, you have closure under addition of the vectors, and scalar multiplication is also going to be inside your set. So these are the three things that make you have a subspace. So, got to have an example. Here we go. Let 1, 2, 3, 0, because I have no imagination, and negative 1, 5, 0, 2 be vectors where? I shouldn't even told you this. Where would the vectors be at? I want you guys to be familiar with this stuff. R who? R4. Each one has 4 components. Does that make sense? So be familiar with your size of your space there. So these are vectors in R4. I want H to be the span of the vectors 1, 2, 3, 0, comma, the vector negative 1, 5, 0, 2. This was on our last test. Let me stop here for a second. Tell me what it means to be in the span. To be in the span, we have a special definition, again, from chapter 1. What was it? What is it? No, not the pivots. Nope, no. To be in the span. We did talk about the number of pivots helped us pick out, what the dimension of it was, but nope. I'm going to talk about the span. Span means linear combinations. Now let's talk about that word. What is linear combination? Yes? All right, so to be inside the span of H, to be inside the span of these two vectors, you can multiply any scalar times the first vector plus any scalar times the second vector, and whatever that covers, that is quote unquote the span of those two sets. The linear combination, scalars times these two vectors gives you the set of vectors inside the set. That's what it means to be inside the span. So scalar multiplication known as linear combinations. You take a combination of a constant times one vector plus a constant times the other vector, and that whole set, any kind of constant you can think of, what set that creates is going to be the space. So here we go. Show that H is a subspace of R4. Prove it. Okay? Well, wait a minute. To prove you have a subspace, what do you have to do? You got to show the zero vectors in there. B, when I add two vectors in there, I got to be back inside of there. And C, any scalar constant times one vector in H has to be inside of H. So, here we go. And I decided, because I need more room than just what I left myself over. All right, you're in trouble because I put the word proof over here. So this is kind of important because I'm setting you guys up with a theorem after this. So here it is. Okay? All right. So the proof is gonna go by the definition. So by the definition, and I'll put my famous DEFN definition, we got part A. Part A was I had to show the zero vectors inside this set. So, again, remember, we have the span of the vectors 1, 2, 3, 0, and -1, 5, 0, 2. This is what we set H to be equal to, the span of these two vectors. I got to show you that the zero vector is inside this set. But the span means that concept of linear combinations. I can pick any constant out there in the real numbers that I can put in front of the first vector and the second vector. But I want to make sure I get the zero vector in there. What's the two constants I want to pick? 0. How about 0 times the vector 1, 2, 3, 0, plus 0 times the second vector, -1, 5, 0, 2. So let C1 and C2 both be 0. You can pick any constant you want to. What is, and this is that linear combination we're talking about. What is 0 times the first vector plus 0 times the second vector? When you add them together, what are you going to get? 0, 0, 0, 0. And that is an element of H. So the 0 vector is in there. It's real simple. All you need is, you can use any constant you want to. I recommend the 0 constant. Does that make sense? All right? Part B. On that definition, what was part B? If since, and I'm going to use my little letters, vector U, let's let that be equal to 1, 2, 3, 0, and vector V be equal to the vector -1, 5, 0, 2. All right? Then we need to show U plus V is an element of H, right? But what is H? H is the span of these two vectors. To show U plus V is inside of H, I recommend let C1 be equal to 1 and C2 be equal to 1. Then 1 times U plus 1 times V, right? That's really what U plus V is. 1U plus 1V is equal to 1 times 1, 2, 3, 0 plus 1 times -1, 5, 0, 2. And that's going to give me this vector here, which is what? 1 plus -1, I believe, is 0. 2 plus 5 is 7. 3 plus 0 is 3. 0 plus 2 is 2. And that element, that vector, is an element of H because it's a linear combination of these two vectors. So I can add two vectors, and being in the span, that's just 1 times the first vector plus 1 times the second vector. That's inside my set. So that puts, thus, U plus V is an element of H. Does that make sense? Now, what was part C? Part C was this. I have to show that any scalar times any one of my vectors is going to be back inside the set. So I'm just going to do arbitrary here. Let C be a scalar inside the real numbers. This is where the Rn comes from. Everything comes from the real numbers here. Okay? And as U is equal to the vector 1, 2, 3, 0, and V is equal to, what was it, -1, 5, was it 0, 2? Then C times U would be equal to C, 2C, 3C, C times 0 is still going to be 0, and C times V would be equal to -C, 5C, 0, and 2C. Okay? and as C times U is equal to C times U plus 0 times V. It's an element of the span of UV, which is what we call H. Reading it just right. And C times vector V is 0 times vector U plus C times vector V, which again is inside the span of UV, which is equal to H. So the constant times U is inside of H, and the constant times V is inside of H. Therefore, by definition of subspace, H, which is equal to the span of UV, is a subspace, and you never end with that. You got to be a sub of somebody, and you have to tell me who that somebody is. Of who? R4. Does that make sense? Don't tell me you just got a subspace. This is a subspace. You got to be sub. That word means you're inside of somebody else. You always have to tell me who that somebody else is. This is a subspace of R4. So that's just a terminology concept here. So, tell me what we just proved. All this beautiful work here, what did we just prove? Well, if I got a set of vectors, and I just used 2 because it was easy, but I could have used 3, 4, 27, 105 vectors or whatever. 2's nice. Okay? I showed that the span of those 2 vectors creates a subspace of whatever set they come from. These vectors here were for vectors in R4. Okay? But I can extend this over. So, what is this telling me? Okay? This is telling me I have a theorem. Okay? And that theorem is this. The span of any set of vectors in Rn will form a subspace of Rn. So you now have it for free that the span of any set of vectors will form a subspace, because we just proved it to you guys. So since I proved it in class, you don't have to prove it anymore. Just remember these words. When I take the span of any set of vectors, I'm going to give you, here's vector 1, 2, 3, here's vector 0, 1, 1, here's vector 4, 5, 6, whatever. The span of those vectors will form a subspace. Always does. Because I just used 2, but you can extend that because of the concept of just a scalar multiples. I mean, it's what does it mean to be in the span? Linear combinations. Well, if you got linear combination of these guys, they're always going to form a subspace. So, and it doesn't matter if it was R4 or R5 or R27 or R3 or whatever, you will form a subspace. So that word span of a set of vectors will always form a subspace. So now we're going to talk about particular types of subspaces. Now remember, we're going to go back to that linear transformation stuff, and any linear transformation can be represented by a matrix. So, first thing we're going to talk about with a matrix, matrix A, we're going to talk about a particular set of vectors being a subspace. We're going to call the subspace the column space. So definition. The column space of a matrix A is the set, and we call it COLA, column space of A, which is all the linear combinations, aka span, of the columns vectors of matrix A. Okay? So, here we go. Here is a matrix. Matrix A is the matrix 1, -3, 4, -4, excuse me, 1, 3, -3, -4, -4, 6, -2, -3, 7, 6. And let's let B be equal to the vector 3, 3, -4. Okay? Question. Is vector B in the column space of matrix A? column space of matrix A? If it is, why is it? Or if it's not, why not? First off, let's talk about what it means to be in the column space. So the question really is this. Is vector B, which is what vector? 3, 3, negative 4. Is it equal to, now what does it mean to be in the space? The linear combinations. I keep drumming that into your head. Space implies for linear combinations of the column space, which is the column vectors of A. So does B, 3, 3, negative 4, equal to C1 times the first column vector, 1, negative 4, negative 3, plus C2 for the next column vector, which is the vector negative 3, 6, 7, plus the third column vector, C3, which is the vector negative 4, negative 2, 6. Okay? And the real question is, for B to be in the column space of A, does there exists a C1, C2, C3 constant scalars such that B is equal to C1 times this vector, I'll call him U1, plus C2 times U2, plus C3 times U3. Can you find me a C1, C2, C3? You see how this is kind of rolling back from all that stuff that we've done before. To be in the column space, you've got to be able to solve for C1, C2, and C3. Does that make sense? So, I have a question for you. How would you do this? How would you find C1, C2, C3? How are you going to do that? Yeah. Outstanding, because you've got a system of equations. So basically you want to find C1, C2, C3. They are the vectors that you're trying to solve for here. So we would do an augmented matrix. That implies that we need to sit there and do 1, negative 4, negative 3, negative 3, 6, 7, negative 4, negative 2, 6, augment with 3, 3, negative 4, and then we go and we're going to go after the old RREF, and let's see what we get. And if I can find a C1 and a C2 and a C3 that works this thing, then the answer is yes, it's in the column space. If I cannot find a C1, C2, and C3, the answer is no. This vector is not in the column space of A. Does that make sense? So, I need a new page here. Luckily, I have plenty of papers here. So here we go. Here we go. So again, I'm going to rewrite this guy over here so we can work it out. I got 1, negative 4, negative 3, negative 3, 6, 7, negative 4, negative 2, 6, augmented with 3, 3, negative 4. All right, help me out here. We need to practice. Never know when you're going to have to do this again. What's your first move? Sweep down. Take that 1. Yes, your Merry Christmas. I gave you the pivot right there, the first one. Sweep down. I got to kill off that negative 4, and I got to kill off that negative 3. So that's 4 times row 1. Add it to row 2. Whatever you add to is what you replace. And 3 times row 1. Add it to row 3. That is going to give me what? First row stays the same. 1, negative 3, negative 4, augment with 3. Okay? Second row is going to be 0. 4 times 3 is negative 12, plus 6 is negative 6. 4 times negative 4 is negative 16, minus 2 is a negative 18. 4 times 3, is 12, and 12 plus 3 is 15. That's my second row. And now positive 3 times 1 plus negative 3 is back to 0. Negative 3 times positive 3 is negative 9, plus 7 is a negative 2. Positive 3 times a negative 4 is a negative 12, plus 6 is a negative 6. And a positive 3 times a positive 3 is a 9, minus 4 is what, 5. I can do What's your next move? You tell me. I would take -6 and make him a pivot. So how would I do that? All right, you want to do it that way, that's fine. Multiply by, how about -1/6? -1/6 times, basically row 2, right? So this would give you what? 1, -3, -4, augment 3, 0, 1, see, 3, and 15 divided by 6 is what? 5 halves. Positive divided by negative is a -5 halves. There you go, -5 halves. Agreed? Okay, and then we got this 0, -2, -6, 5. What's your next move? Sweep down. 2 times row 2, add it to row 3, replace row 3. So this is 1, -3, -4, augment 3. 0, 1, 3, -5 halves. 0 times 2 is 0 plus 0 is still 0. 0 times 1 is, so 2 times 1 is 2 plus -2 is 0. 2 times 3 is 6 plus -6 is 0. And 2 times -5 halves is -5 plus 5 is 0. I got a row of zeros. Well, let's go for that RREF. So I got one more move to make. What's my last move? Take that pivot now and sweep up. So to sweep up, I'm going to do 3 times row 2, add it to row 1, and replace row 1 with that. So 0, 0, 0, augment 0. 0, 1, 3, -5 halves. Here we go. 0 times 3 is 0 plus 1 is still 1. 3 times 1 is 3 plus -3 is 0. 3 times 3 is 9 plus -4 is what? 5. All right, here we go. Let's see here. 3, make sure I don't screw up my math on this fraction here. 3 times -5 halves is -15 halves. And -15 halves plus 3, we're going to go for a calculator on this one so I don't screw it up. All right. 3 times -5 halves plus 3 is -4.5, otherwise known as -9 halves. So this would be a -9 halves. This is in, you should recognize him, it was a question on your last test. It is in RREF format. So, again, we need to solve for C1, C2, C3. What's the answer? Well, I'm going to write these back as equations in terms of my C's. This was the column of C1, C2, and C3. So C1 plus 5C3 is equal to a -9 halves. C2 plus 3C3 is equal to a -5 halves. Solve for the pivots. C1 is equal to -5C3 minus 9 halves. C2 is equal to a -3C3 minus 5 halves. And C3 is not a pivot. He is free, which means he's what? Free variable, he equals himself. So, my answer for finding the C1, C2, C3, C1, C2, C3 is equal to -5, -3, 1 times C3 plus -9 halves, -5 halves, and there is no constant there, 0. Oh yeah, what was the question? Let's go back to the question. Question. Is vector B an element of the column space of A? That's the question. Yes or no? You tell me. I got a no, shaking a head no. I got a yes. Okay.
No.
Got a no. Tell me that type of solution right there. Is it, quote, consistent, unique, consistent, infinite, or inconsistent? Tell me. consistent what? Infinite. There's an infinite number of these guys. What does that mean? Your words here. Consistent, infinite. So what does that mean in English? Consistent, infinite. There is an infinite number of solutions. So for B to be in the column space of A, there has to be a solution. What are you telling me? How many solutions you got? Infinite number of solutions. So is B element of column space of A? There's an infinite number of solutions. All you need is one, but there's a lot of them out there. All you need is one. Since there's a lot of solutions, quote my words, a lot of solutions means yes, it is. It's not unique. You let C be 0, let C be C3 be, C3 be 0, C3 be 1, C3 be 405. You can get an answer for C1, C2, C3. That infinite number of solutions, it still is consistent. So the answer is yes, B is in the column space of A.
So as long as there are one solution.
At least, better word, at least one solution, the answer is going to be yes. So here, let's go with that. When would it not be in the column space of A? What would you expect to see on this crap matrix stuff that we're doing here? And what is inconsistent going to look like? Over here, 0, 0, 0, something that's not 0. All right, number, right? That's when it's not going to be. So you can look at this thing and go, oh, this is not an inconsistent case. Consistent infinite or consistent unique means yes. Inconsistent is the only time it's not going to be an element. Does that make sense? Cool. Well, I got 3 minutes left. I can do this. All right. If you happen to have a column space, what is the next major obstacle here? Definition. Space. We're looking at the columns of matrix A, right? Well, just as easily, we can look at the rows of matrix A and look at those guys as vectors. And that is called the row space. The row space of a matrix A is called row A, because we're math people, we don't really think too deep into how we call this stuff. ROW-A, the row space of A, which is the set of all linear combinations, aka the span, of the rows of vectors of matrix A. But you guys have been beat to death that always been focusing on the columns, right? Column, column, column. We always look at the columns because that's where the vectors usually show up at. So, but we can talk about the row space. These are the rows. So with that concept, if you are concerned about actually trying to do rows, because they're going to look very long equations, because C1 times row 1 plus C2 times row 2, you're going to run out of paper on this thing. Here's the deal. The row space of A is going to be the same thing as the column space of A transpose. What was A transpose? You take all the rows, turn them into columns, so then you can turn the rows into columns, but that's on the A transpose. So we're going to do the exact same thing, but you would do it on A transpose. Does that make sense? Okay? So we don't do very much with this concept here, because we just say that the row space will be the same as the column space of A transpose, and we do the same thing we just did. Yes? Yep. Once you've done your work, yes. But all the work will be in that transpose because you're so used to doing columns. You can still do the same columns, but once you're done, so let me go back over here. Once you're done with this thing type thing here, you would flip them back up and make it C1, C2, C3 times this vector times C3, this vector, and you write them back as rows. Yes. So if you got this thing right here, you can go back and write them back as rows and stuff like that instead of columns. These are the columns, so it'll be 1, 0, 0, 0, you can write them back as rows. So you go back and forth with this thing. Now, with that being said, there's one other space here called the null space. Now, the null space is this. The null space of a matrix A is the set, null A, again, we're math people, don't think too deep. We got col A, row A, and now null A, which is the set of all solutions of the homogeneous equation. Now, what is a homogeneous equation? You set the matrix A times X equals 0, and you solve for X. So we're going to go back to our happy world here. We've been doing this since day 1 in this class. Matrix A times X, set it equal to 0, and go solve. How many different ways I can get an answer here? Well, There's always, remember, when you have a null space, there's always one vector that's gonna be in there. What vector is that? The zero vector. What is 0 times matrix A always gonna give you? 0. So this guy always has an answer. You won't get the inconsistent system here. Does that make sense? You're gonna have at least one vector. 0 is gotta be in there. But maybe there's more vectors in there. When there's free variables and stuff like that, then you can get a lot of different kind of answers and stuff like that. So, question for you. The null space of an M by N matrix is a subspace of Rn. Why? A is M by N. You multiply it times vector X. It's a vector, so it's by 1, but who is this guy gotta be? What has to be the entry right there? What size does it have to be be able to multiply a matrix M by N by this vector, somebody by 1? It's gotta be an N. And so X is gotta be an element of Rn, right? So X, these solutions, which is the solutions, are gonna be inside of Rn. So these X's are gonna be a subspace of Rn. That is why. You're gonna come from Rn. So even though this is M by N, the reason why the set of solutions have to come from Rn, because this is M by N, X, what you're trying to solve for is N by something or other, which is a vector inside of Rn. And then the linear combinations of those X's inside of Rn makes that subspace. Yes? Yep. Okay, run that by me again.
So you said like X vector is within Rn.
Yes.
Automatically mean that that's the subspace too?
Yes, because remember, these guys, it could be the 0 vector, and that's all you got, but maybe it's another vector. But remember, it's gonna be, you're solving for these guys, so there are gonna be some free variables on this thing, and a free variable is always that linear combination. So go back and look at this guy again over here. See, forget there's no constant over here. It's a constant times this. That's a linear combination. So any vector is going to be the span because you're going to have a free vector, unless you've got 0, 0, 0. Well, and you can do linear combinations. What's the linear combination of 0? It's still 0. So that still will be within the span of these set of vectors is going to be inside of Rn. Okay? So we'll pick this up next time with the basis concept. And we'll pick this up next time, but enjoy your fall break. And remember, your homework from 2.1 to 2.5 is due on Thursday. See you guys then.